Ideal diodes. Now, when we solve a problem or circuit, we always try to approximate what the diode should look like. And there's three different approximations. So first, we're going to look at the first approximation. The first approximation, we approximate the diode to have a value of no current going through it. When the voltage is 0, the current goes straight up in the air. That's called the first approximation. So basically, that diode is operating like a switch. That's what it looks like. If you have a voltage source here, like if you take this circuit, of some voltage source, a resistor, and a diode here, we are approximating this. When you do first approximation, we're saying this diode works like a voltage source here of the value of V with the switch that's open and at t equals to 0, that switch comes down and closes. So the voltage across this diode is actually 0. So if we give some numbers here, let's say we have this voltage to be 5 volts. And this is 5 here. And this resistor is 10 ohms. So what is the current going through that? Using the first approximation, the current's going to go this way. Now it's plus to minus. It's forward biased. That current, so my circuit will look like this. 5 volts. $10. And a voltage here of 0. A voltage drop here of 0. So if this is ground here, then that means the voltage here is 0. We're saying the minute this voltage is more than 0, boom, this one breaks and that voltage here is 0. That current here has to be I through the diode, has to be 5 minus 0 divided by 10, which is 1/2 amp. That's not really true there, but that's the first approximation that people use. Not a good approximation. So then what's the second approximation? The second approximation, we're going to take that diode and replace it with what? The same as the first approximation, except instead of that current start to go through it at 0 voltage, the current actually is going to go through it at 0.7 volts. So at 0.7 volts, which is VNE for silicon, we're talking about silicon here, 0.3 for germanium, the current will go through it. So if we go back to that first circuit that we had here, that 5 volts here, and that's the 10 ohms, and that's the diode here. Since this voltage is much larger than 0.7, it's going to force this to go through it in this direction. It's forward biased. So this will be 5 volts, 10, and this diode now will have a voltage across that of 0.7 volts if it's silicon. So if this is your ground, this voltage here is 0.7 volt. So what is the current going through it here? What's that I through the diode? It's a little bit less. 5 minus 0.7 divided by 10, and that's what? 4.3 divided by 10, which is 0.43 amps. Notice in the first approximation that current was 0.5. Half an amp is 0.5 amps. In the second approximation, that current is actually 0.43 amps. It's still not good. I mean, it's a good approximation. We use that a lot, actually. But if you want to get the real value, then you want to use the third approximation. And what's the third approximation? And that's when you replace, so this is my second approximation. So let's look at the third approximation. The third approximation we're going to replace actually that Xeno diode with this graph. And this is the 0.7 for silicon. Remember in the second approximation, look at the 0.7. The current's going straight up in the air. Straight up there. So in the third one, the current is going to go which way? It's going to be pointing upward. It's going to go that way. So what does that mean, it was pointing that way? That means we're going to actually replace the diode. We're going to take this diode and replace it with a diode or a voltage source if you want to. We're going to replace it with the, I said a voltage source, now I do a resistor, with the voltage source of 0.7 with a resistor with that, and a small resistor. And this is the first time we're seeing the resistor. So how big that resistor? Well, with most diodes, that resistor is very small. That's called RB, R bulk. So what's the R bulk here? If you remember, actually, you have two pieces of silicon there. You have a positive side and you have a negative side. So the R bulk is equal to the R of the positive plus the R of the negative. Again, RB stands for bulk resistor. And again, how big that resistor? Roughly about 0.23 amps, 0.2, 0.3 amps. Is really small. So RB is very small. It's approximately 0.23 ohms for most actually of these diodes, and some even less. So when you're looking for the voltage across the diode is no longer 0.7. The voltage across the diode is going to be the 0.7 plus the drop across that one, which is I sub D times R sub bulk. You multiply them out, and that will give you the value. Now, do we have to count that R sub bulk? Do we have to worry about that resistor? Well, here's the rule. If R sub bulk is less than 1/100th of R Thevenin, we neglect that. It's not going to make any difference. So if R sub B is less than 0.001 R Thevenin, 001, I'm not focused today, R Thevenin, then we can neglect R sub B. So let's take an example. Let's take a voltage source of 10 volts, and let's take a diode here. Let's take the N4001 diode. Those actually have a small value of R sub B. And you have R sub L here equals 1,000, 1 kilo ohm. So if I'm doing third approximation, I'm going to take this diode here and replace it with 10 volts, 0.7 volts, with R for the diode. So this is my diode right there. And for that diode, roughly R is about 0.2. and this is R sub L, which is 1,000 ohm. So if you think about it, these two guys connected in series. Is it really going to make a difference if you add the 0.2 or not? So this will look like a one voltage source, if you're looking for the current through that, of the value of 10 minus 0.7, which is 9.3 volts. And that resistor here is 1,000.2. Big deal. That 0.2 does nothing. So I sub D is going to be 9.3 divided by 1,000.2. And if we do the math there, that's 0.0093 amps. So what happens if I didn't count the 0.2? So if I don't count the 0.2 ohm, then I sub D will be the 9.3 volts divided by 1,000. Guess what the answer is? Still 0.0093 amps. This number is more than 1,000 times bigger than this. Actually, 5,000 times bigger than this. We said as long as this number, or this number is 100 times bigger than this, is not worth adding. So I did it both ways just to show you. It really doesn't make a difference putting that in or not. Now on the other side of it, if I do the same thing but I make that 5 ohms, then it will make a difference. So let me do that with a small value here. Same circuit, 10, the same diode, N4001, and let's make R sub L equals 5 ohms. So now what's the current? So that will be 10. I'm going to put a 0.7 here for that diode, silicon. I'm going to put a resistor of 0.2, and that's my 5. So if I simplify this, that's what? 9.3 and 5.2 ohms. And what is I sub D? I sub D equals to 9.3 divided by 5.2. And let's see what the calculator says here. $9.3 divided, I'm going to turn the calculator on. 9.3 divided by 5.2 equals 1.7885 amps. Now what happens if I don't include the 0.2 in this example? Well, I'm going to get a different number. If you don't include the 0.2, no, don't, here we go, include the 0.2 ohm. So what makes it, if I don't include the 0.2 ohm, what will happen? I sub D will be what? 9.3 divided by 5, which is what? 9.3 divided by 5, and that's 1.86. Notice there's a difference in that current going through it. So in that resistor, it's not 100 times bigger than this. I can't really not count it, so I have to count that. So in this case, this will be the wrong answer. That would be the correct answer. So that's how you decide actually if you're going to include that resistor, the 0.2 or not. So for ideal approximation, that's what we do. Non-ideal, we use the 0.7 and the 0.2. For ideal, we just drop this and use 0.7 and do the calculation that way.